Right now, in a sealed lab, a cloud of atoms sits a hair above absolute zero, and it is the hottest thing on Earth. Hotter than fire, hotter than the sun, hotter than infinite heat itself. Everything you were taught about temperature is about to break. We will cross a boundary beyond infinity, watch heat flow the wrong way, and touch the same strange force pulling the universe apart. If cosmic mysteries thrill you, a quick like and subscribe fuels this channel. Prepare yourself. We begin. Hold your hand close to a candle and you feel warmth crawl across your skin. That warmth feels like a thing, a substance, something the flame is pouring into you. For most of human history, that is exactly what people believed. They imagined heat as an invisible fluid that leaked out of hot objects and soaked into cold ones. They even gave the fluid a name and drew diagrams of it flowing like water. Whole textbooks were written about this invisible substance of heat. They were wrong, and the truth turned out to be far stranger. Temperature has almost nothing to do with what your skin reports. Reach into a hot oven and the air feels blistering, yet that air carries surprisingly little heat. Brush the metal rack inside for half a second and you get burned instantly, even though the rack and the air share the exact same temperature. Your skin measures how fast energy floods into you, not the real amount of heat waiting there. Your skin, put simply, is a liar, so what is temperature truly? Picture the atoms inside anything near you. The wood of a desk, the water in a glass, the air in the room. Every one of those atoms is trembling, jittering, bouncing in place like a crowd of restless kids who cannot sit still. In a cold object, the trembling stays gentle and slow. In a hot object, the trembling turns fast and violent. Temperature is a scorecard for that hidden motion. Raise the temperature and you crank up the jiggle. That single idea rebuilt all of physics. It meant heat was never a fluid. It was movement, shared across countless particles far too small to ever see with your eyes. Now push the picture one more step because the real machinery hides here. Temperature belongs to a crowd, never to one atom alone. A single atom has no temperature. The word only means something for a giant swarm of particles, and it describes how the total energy gets divided among them. Imagine a stadium packed with 100,000 fans, and imagine energy as tickets handed out through the seats. Temperature tells you the pattern of how those tickets spread through the rows. At a low temperature, almost everyone crowds the cheap seats near the bottom, each holding barely any energy. Hand the crowd more energy, and fans begin climbing toward the higher, pricier rows. The hotter it gets, the more the crowd spreads upward and outward, filling seats farther and farther above the floor. This picture feels comfortable, familiar. It seems to explain everything you have ever touched, from an ice cube to a roaring bonfire. Yet buried inside this friendly stadium sits a trapdoor, a loophole hidden in the rules that decide how energy spreads through a crowd. Follow that loophole far enough, and you reach a place that should be impossible. A place hotter than fire, hotter than any star, hotter than a number your mind can even hold. To find the trapdoor, we first have to visit the one temperature everyone treats as the end of the road. The coldest cold. The floor beneath every floor, where motion itself is supposed to freeze and stop. Everyone has heard of it. Almost no one asks the obvious question that comes right after. Absolute zero is the coldest anything can ever be. Scientists pin it at around minus 460 degrees on the Fahrenheit scale. Colder than deep space, colder than the darkest gap between the stars. At that point, the trembling of atoms slows almost to a standstill, and the jiggling crowd finally holds still. There is no seat lower than the floor, so there is nowhere left for the energy to drain. That is why nothing can ever be colder. You simply run out of down. Nothing anywhere has ever been measured below it. Physicists chase this floor with obsessive patience. In laboratories around the world, teams cool tiny clouds of atoms to within a whisker of it, reaching temperatures a few billionths of a degree above the limit. They build the coldest spots in the entire known universe, colder than anything nature makes on its own. And every time they get close, absolute zero refuses to be reached. It stays a wall you can approach forever without touching, like a runner who halves the distance to the finish line with every step and never arrives. So the coldest possible cold has a clear meaning. It is the bottom of the ladder, the place where motion runs out. Here is the question almost nobody thinks to ask. If cold has a floor, does hot have a ceiling? Stop and sit with that for a moment. Everyone knows the cold end stops. It stops at absolute zero. and it stops for a reason you can picture, because the jiggling cannot slow below stillness. But the hot end feels different. The hot end feels open. You can always heat a thing a little more, light a match, and the flame runs about 2000 degrees. A blowtorch pushes hotter. The surface of the sun blazes at roughly 10,000. The core of the sun roars past 27 million. A supernova climbs into the billions. A collision of two dead stars can spike hotter still, into the trillions, for a brief and violent flash. Every step you can imagine one hotter. The ladder of heat seems to stretch up forever, with no top rung in sight. Add more energy, and you always get a higher number. For a long time that felt like the whole story. Cold has a floor, hot has no ceiling, case closed. But that neat little picture hides a crack, because temperature, remember, is about a pattern. More than about the raw amount of energy inside a thing, it is about how energy spreads across a crowd of particles, and patterns can do things that raw amounts of energy cannot. Change the rules of the crowd, force the energy to spread in a way nobody expected, and the meaning of hot begins to warp. The ladder of heat stops behaving like a simple ladder. Somewhere up near the top, the rungs bend back on themselves, and the whole idea of hotter and colder twists into a shape that should not exist. To see how the ladder bends, we have to look closer at what temperature is measuring underneath. Something deeper than the jiggling. A hidden quantity that decides which way heat is allowed to flow, and it hides one secret that unlocks the entire mystery. Underneath temperature sits a second idea, and it runs the whole show. Physicists call it entropy. The word sounds intimidating, so throw the word away and keep the picture. Entropy is simply a count of how many ways you can arrange something, how many different patterns look the same from the outside. A tidy desk has low entropy, because there is basically one way for everything to sit in its correct spot. A messy desk has high entropy, because papers and pens can scatter in a billion different arrangements, and it still looks like the same mess. Nature loves high entropy. Left alone, everything drifts from tidy toward messy, from few arrangements toward many. The universe forever slides toward more ways of being arranged, because there are simply far more messy patterns than tidy ones, so messy wins by sheer numbers. Now connect entropy back to energy, because that link is the master key to this entire story. When you pour energy into an ordinary object, you hand its atoms more ways to arrange themselves. More seats open in the stadium, more rows become reachable, the crowd can spread into a larger number of patterns, so adding energy adds entropy. More energy, more mess, more possible arrangements. That relationship is the true definition of temperature. Temperature measures how much extra disorder you unlock for each drop of energy you pour in. When a tiny bit of energy buys a big jump in disorder, the temperature reads low. The system is hungry for energy and grabs it eagerly. When the same drop of energy buys only a small jump in disorder, the temperature reads high. The system already brims with energy and barely cares about a little more. Picture it as an exchange rate at a currency booth. You bring energy to the counter, the booth pays you back in disorder. A cold object runs a generous booth, handing out heaps of disorder for a single coin of energy. A hot object runs a stingy booth, offering barely a scrap of disorder for the same coin. Temperature is nothing but that exchange rate. The rate of disorder gained per unit of energy spent. This is the deepest truth about temperature, and it sounds nothing like the warmth on your skin. Temperature is a slope. It measures how steeply disorder climbs as energy climbs. Steep slope, low temperature. Gentle slope, high temperature. Now watch what this hands us. Heat always flows from hot to cold, and this exchange rate explains exactly why. Energy drains out of the stingy booth and into the generous one, because the universe can buy far more total disorder that way. The generous booth turns each coin into a mountain of arrangements, so energy slides downhill, from high temperature to low, until both booths offer the same rate and the trading stops. Everything about heat, every furnace and freezer and cup of cooling coffee, obeys this one rule. Disorder climbs with energy, and temperature is the slope of that climb. But a slope can do something a simple ladder cannot. A slope can flatten out, and in the right kind of system, a slope can even turn around and point downhill. If disorder ever started to fall as energy rose, the exchange rate would flip. The slope would reverse, and the temperature, that innocent little slope, would do something no thermometer was ever built to show. To understand how a slope could possibly reverse, we first have to see why, in ordinary matter, it never, ever does. In everything you have ever touched, that slope only ever points one way, up. Pour energy into a rock, a gas, a puddle, a person, and the disorder inside always climbs, never falls. The exchange rate stays generous or stingy, but it never flips its sign. That is why ordinary temperature stays stubbornly positive, from the coldest frost to the heart of a star. The whole world you know is locked on the same side of the rule. The reason hides in one simple fact about ordinary matter: its energy has no ceiling. Think again about atoms flying through a gas. Their energy lives mostly in motion, in speed, and speed has no upper limit built into it. An atom can drift slowly, or race, or scream along faster still. There is always a quicker speed available, always another rung above the last. The ladder of motion climbs forever with no top, exactly like the ladder of heat seemed to in the beginning. Because the energy can climb without limit, the disorder can climb without limit too. Give the gas more energy, and its atoms spread across an ever wider range of speeds. Slow ones, medium ones, fast ones, blistering ones, all mixed together in a growing sprawl of possibilities. More energy always cracks open more room, more arrangements, more mess. The slope never runs out of up. Picture that stadium again, but now imagine it has no roof and no highest row. The seats just keep going up into the sky forever. No matter how many tickets you hand out, the fans can always climb higher, spreading into fresh seats that stretch endlessly overhead. You can never crowd the top, because there is no top to crowd. The higher you push the energy, the more the crowd fans out, and disorder keeps rising with every ticket. That endless staircase is the trap. It guarantees that adding energy always adds disorder. It guarantees the slope always points up. And it guarantees that ordinary temperature can never turn negative, no matter how absurdly hot you make it. You can reach 1,000,000 degrees, 1,000,000,000, 1,000,000,000,000. The number grows without bound, yet it always stays on the positive side, always climbing, always pointing up the endless stairs. So the hot end of the ladder truly does stretch up forever, for anything built the normal way. The ceiling everyone assumed was missing really is missing, as long as your system can always store a little more energy in faster motion. Here is the crack that changes everything. That endless staircase is a property of ordinary matter, rather than a law of the universe. It comes from the fact that motion has no speed limit, so energy has no upper wall. Take that assumption away, and the whole picture shatters. Imagine a system where the energy does have a ceiling, a hard maximum, a highest possible rung, a top row in the stadium beyond which no fan can climb. In that world, the endless staircase becomes a staircase with a final step, and a staircase with a final step behaves in a way that will bend your mind, because once the crowd starts crowding that top row, disorder stops rising and begins to fall. Such a system sounds impossible, a box of energy with a lid. Yet nature builds exactly that, in more places than you would ever guess. Find one, and you have found the trapdoor. And what waits on the far side of that trapdoor breaks the meaning of hot. To break temperature, you need a system with a top, the highest possible energy, a rung above which nothing can climb. That single requirement changes everything, so hold on to it. Ordinary matter fails the test because motion can always speed up and store more energy. What you need instead is a system where energy is capped, a container with a lid welded on. Fill it, and eventually you hit the top, with nowhere higher to go. Nature does build such systems, and the cleanest example lives inside atoms themselves. Many particles carry a property called spin, and the simplest version acts like a tiny compass needle. It can point in only two directions. Line it up with a magnetic field and it sits in the low energy state, the comfortable one, like a compass resting where it wants to rest. Flip it against the field and it climbs into the high energy state, fighting the pull, like a compass forced to point the wrong way and straining to snap back. 2 positions, 2 rungs, that is the entire ladder. Low energy at the bottom, high energy at the top, and absolutely nothing above. The lid is welded on by the laws of physics, because a 2-way compass has no third direction to store extra energy in. This is the ceiling that ordinary matter never had. Now walk energy up this tiny 2-rung ladder and watch the disorder, because here the slope does something forbidden. Start cold with the field switched on. Nearly every little compass lies down in the low seat, all pointing the same easy way. One tidy arrangement, low disorder. Now feed the crowd some energy. A few compasses flip up into the high seat. The population mixes, some down and some up, and the number of possible arrangements explodes. Disorder climbs, exactly as expected. So far the slope points up, and the temperature stays positive and normal. Keep feeding energy, and you reach a special moment. Half the compasses point down, half point up. This is the messiest possible mix, the arrangement with the most ways to shuffle it, the very peak of disorder. The exchange booth is running at full tilt. Then something strange begins. Push past halfway and the crowd starts crowding the top seat. More compasses point up than down. And now, as you keep adding energy, the mix grows tidy again. Fewer and fewer ways to arrange it, because the crowd is bunching into that single high row. Disorder starts to fall. Read that again slowly, because it is the whole secret. You're still pouring energy in, but the disorder is going down. The slope has flipped. The exchange booth has started paying you less disorder for each coin, and then less, running backward. By the definition we built, that flipped slope is a negative temperature. Energy up, disorder down, and the innocent little slope points the wrong way. None of this can happen without the ceiling. The welded lid is what forces the crowd to bunch at the top. Without a top row, the crowd would just keep climbing forever and the slope would never turn. The ceiling is the trapdoor, and we have just watched it open. But watching a slope flip is one thing. Believing that the atoms sitting on that flipped slope are truly hotter than any fire is another. To feel why, we have to look at that strange upside-down crowd where the top of the stadium is fuller than the bottom. Look closely at what just happened, because it turns the stadium on its head. In every normal object, the bottom seats stay the crowded ones. Most atoms hold low energy, fewer hold high energy, and the numbers thin out as you climb. That is the natural shape of a warm crowd. Heavy at the bottom, sparse at the top, like sediment settled in a jar. Physicists see this shape everywhere, in every gas and solid and star, and they can read a temperature straight off how quickly the crowd thins toward the top. Now flip it. In our little compass system past the halfway point, the top seats hold more members than the bottom seats. The high energy state is the crowded one. The pattern stands upside down, heavy at the top, sparse at the bottom, like sediment that somehow floated up and packed itself against the lid. Physicists have a name for this backward shape: population inversion. The population of the crowd has been inverted, turned over, flipped from its natural settling, and a crowd shaped like that cannot be described by any ordinary temperature. No positive number can draw a crowd that is heavier at the top. The math simply refuses. Try to force it. Ask what temperature would pile more atoms into the high seats than the low ones, and the equation spits back a number below zero. A negative temperature. The upside-down crowd and the negative sign are the same fact wearing two costumes. Here is the picture to hold. Imagine a waterfall running upward. Imagine a jar where the heavy grains float and the light ones sink. Imagine a stadium where the nosebleed rows are jammed while the front seats sit empty. Every one of these is impossible for ordinary stuff, and every one is exactly what a negative temperature system looks like from the outside. The crowd has climbed to the top and refused to come down, and the crowd can only do this because of the ceiling. Remember, the seats stop. There is a top row and nothing above it, so when you jam energy in, the crowd has nowhere higher to flee. It piles against the lid, thick and packed, and the natural bottom-heavy shape turns over. Give an ordinary gas that much energy and its atoms would just fly off into ever-faster motion, spreading up an endless staircase, staying bottom-heavy forever. Only a capped system can invert. So a negative temperature is a real physical arrangement of real particles, far from some abstract minus sign scribbled on a chalkboard. A crowd that has flipped upside down and crammed itself into the higher seats it is allowed to reach. You could, in principle, take a photograph of it. You would see the impossible waterfall frozen in place. This upside-down crowd holds more energy than any right-side-up crowd ever could because it has stuffed its members into the highest seats available. It is by any honest measure of energy content as loaded as the system can possibly get. Bursting, maxed out, straining against its own ceiling, which raises the question that snaps this whole story into focus. If a negative temperature crowd holds the most energy possible, then in the language of heat, what is it? Cold, because of the minus sign in front? Or hot, because it is packed to the brim? The answer flips everything you believe about the words hot and cold. And to reach it, we have to follow the temperature dial as it climbs all the way to infinity, and then keeps going. Follow the temperature as we heat that little compass crowd, one careful step at a time, and watch the dial do something no thermometer was built to survive. Start cold. Almost every compass lies in the low seat. The temperature reads a small positive number, cool and ordinary. Feed in energy. Compasses flip upward. The temperature climbs. 10 degrees, 100, 1,000, on and on, all positive, all normal. The crowd is spreading, disorder is rising, the slope points up, and everything behaves. Keep going. Push toward that special halfway point, where exactly half the compasses point down and half point up. This is the peak of disorder, the messiest possible mix, and as you approach it, the temperature does not settle on some large number. It races upward without limit. 1,000 degrees, 1,000,000, 1,000,000,000. The dial spins faster and faster toward a value too big to write. At the exact halfway point, the temperature hits infinity. That is a real result of the math, as literal as any equation. When the crowd is split perfectly even, when adding a scrap of energy changes the disorder by essentially nothing, the slope goes flat, and the exchange rate reads infinite temperature. The system is so hot that it no longer cares at all which seat its members take. Up, down, it is all the same, perfectly indifferent. Maximally hot in the ordinary sense. You might think that is the top. The end of the ladder, infinity, the final rung. Watch what the dial does next. Push one more scrap of energy in, past the halfway point into the upside down crowd. Now more compasses point up than down. Disorder begins to fall, the slope flips, and the temperature, which was sitting at positive infinity, does not climb higher, because there is nothing higher than infinity. Instead, it reappears on the other side. It comes back as negative infinity, and then it climbs. Negative infinity, negative 1,000,000,000, negative 1,000,000, negative 1,000. The dial rises through the negative numbers, heading toward -0. Trace the full journey. The temperature climbed from a small positive number up to positive infinity, vanished off the top of the scale, and returned from negative infinity, rising towards 0 from below. The dial wrapped all the way around like a clock hand sweeping past 12 and coming back to 1. This is the trapdoor, drawn as a picture. Temperature is a loop with a break in it. On the ordinary side, cold is a small positive number and hot is a large one. Then the scale rips open at infinity, and on the far side, the numbers come back negative, running from negative infinity up toward -0. Which means the coldest thing in the whole scheme is a small positive temperature, near absolute 0. And the hottest thing of all, the very top of the entire loop, is -0. The negative temperatures do not live below the cold end. They live above the hot end, past infinity, on the far shore of a scale that wrapped around on itself. So a negative temperature sits beyond the hottest positive temperature you can name, far past a little bit of cold, beyond infinity itself. That single fact rewrites the meaning of hot and cold, and almost everyone gets it exactly backward. To see just how backward, we have to place negative temperature in the true order of heat and prove that the atoms in that lab are hotter than the sun. Here is the line that breaks most people. A negative temperature is hotter than any positive temperature. Full stop. The minus sign fools everyone. See a temperature below 0 and your brain screams cold, freezing. A winter night, a block of dry ice, the dark of space. But that instinct comes from the Celsius and Fahrenheit scales, where below 0 really does mean chilly. On the absolute scale, the one physics actually uses, the rules are different, and on that scale, negative does not mean cold, it means beyond the top. Rank every temperature in the true order of hotness, from coldest to hottest, and the ladder looks bizarre. Start at the coldest, a tiny positive number just above absolute 0. Climb up through ordinary warm numbers, keep climbing to 1,000,000, 1,000,000,000, all the way to positive infinity. Then, Past infinity, cross over to negative infinity. Then climb again, through negative billions and negative millions, up toward negative zero, which sits at the very top as the hottest state of all. So the honest ranking runs like this. Cold is a small positive number. Hotter is a big positive number. Hotter still is positive infinity. Hotter than that is negative infinity. And the hottest possible is negative zero. The negatives are the penthouse, stacked above infinity, high above the basement. The physicists who first stumbled onto this said it plainly. A system at negative temperature is extremely hot, the very opposite of cold. Put it next to any ordinary object, and heat pours out of the negative temperature system into the ordinary one, never the other way. It behaves like the hottest thing in the room, because it is. Feel why through the exchange booth. Heat flows from the stingy booth to the generous one, from high temperature to low. A negative temperature system runs a booth so far past stingy that it pays out negative disorder. It is more grasping with its energy than any positive temperature furnace could ever be. So when it touches anything ordinary, energy gushes out of it, downhill into the cooler, positive world. That gushing outflow is the signature of something searingly, impossibly hot. Picture the strangeness. Set this atom cloud beside a burning candle. Heat does not crawl from the flame into the cloud. Heat crawls from the cloud into the flame. The cloud, sitting a hair above absolute zero on your everyday thermometer, would try to warm up the fire. It is, in the only sense that governs the flow of heat, hotter than the flame, hotter than the blowtorch, hotter than the surface of the sun, hotter than a number you could ever finish writing. That is the shock hiding inside the phrase negative temperature. These are not frozen atoms. They are the hottest atoms ever prepared by human hands, sitting quietly in a lab, colder than deep space on one scale, and hotter than the stars on the scale that truly matters. For decades, this lived mostly as a strange line in physics textbooks. A loophole people knew was real but rarely built. Then a handful of experiments dragged it out of the math and into glass chambers and laser light, and made the impossible crowd stand up in the real world. The story of how humans first caught a negative temperature begins with a quiet prediction, made by a man who spent his days studying whirlpools swirling in a moving fluid, far from any atom. In 1949, a chemist named Lars Onsager stood up at a conference and said something almost no one was ready to hear. Onsager was not studying atoms or magnets or heat at all. He was studying the swirling chaos of a moving fluid, whirlpools, vortices, the little spinning eddies you see when water rushes past a rock or when cream twists into coffee. He was trying to understand how those swirls behave when you crowd many of them together in a thin sheet of fluid, packed onto a flat surface with nowhere to escape. And he noticed something that stopped him cold. In a thin, bounded sheet of fluid, the swirling energy has a ceiling. The vortices can only spin so wildly, arrange themselves in only so many ways, before they run out of room. The energy is capped, just like the energy of those little two-way compass needles would be capped years later. Onsager was staring at the very ingredient that unlocks the trapdoor, a system with a top. So he worked through the consequences, and the math handed him the impossible answer. Above a certain energy, the vortices would organize themselves into large, calm, long-lived swirls. The disorder would fall as the energy rose, the slope would flip, and the fluid, by every honest definition, would sit at a negative temperature. Onsager understood exactly what he had found. He wrote that such states correspond to negative temperatures, and he saw that they explained a genuine puzzle. Why do big storms and giant whirlpools sometimes gather themselves out of smaller chaos, instead of just dissolving into finer and finer mess? Because a bounded, swirling fluid can climb past infinity, invert its crowd, and settle into those huge, orderly, negative temperature swirls. It was one of the first times anyone had pointed at the real world and said, "There, that thing, that is a negative temperature." And almost nobody paid attention. The idea sat in the corner of physics like a curiosity, too strange to trust, too abstract to test. A brilliant man had predicted a temperature beyond infinity, and the world mostly shrugged. Part of the problem was that vortices in a fluid are messy, hard to control, hard to measure cleanly. You could not easily hold one still and read its temperature off a dial. The prediction was gorgeous, but it floated in theory, waiting for someone to catch it in a form you could actually pin down and study. Onsager himself was the kind of mind that saw these things early and often alone. He would later win a share of a Nobel Prize, and he built a reputation for insights so far ahead that colleagues needed years to catch up. His whirlpool prediction was one of those insights. A door pushed slightly open, with no one yet willing to walk through. The idea needed a cleaner stage. It needed a system simple enough to control atom by atom, with a ceiling you could count on, and a crowd you could flip on command instead of a churning fluid full of swirls too tangled to track. Something a physicist could cool, prod, measure, and trust. That cleaner stage arrived only 2 years later, in a laboratory at Harvard. Two scientists took a small, ordinary-looking crystal, slid it into a magnetic field, and prepared to do something to the atoms inside that had never knowingly been done before. They were about to flip a crowd upside down on purpose and catch the first negative temperature humans ever made. In 1951, two physicists at Harvard decided to chase the impossible over a single weekend. Their names were Edward Purcell and Robert Pound, and they were masters of a young technique for peering inside matter using magnetic fields and radio waves. They knew how to reach into a solid and speak to the tiny spinning cores of its atoms, the nuclei, each behaving like a minuscule compass needle, and they had a hunch about what those needles could be made to do. The material they chose sounds almost boringly plain. A small crystal of lithium fluoride, a simple salt built from lithium and fluorine. But inside that chip sat a vast orderly army of nuclear compass needles, all able to point along a magnetic field or against it. Two seats, a low one and a high one, a ceiling welded on by nature. The perfect stage Onsager's whirlpools never quite offered. Here is the setup. Purcell and Pound placed the crystal in a strong magnetic field and let it settle. The little nuclear needles lined up mostly in the low seat, pointing the comfortable way, cosy and cold and ordinary. A tidy, bottom-heavy crowd, exactly as any warm object should be. Then they did something sudden and clever. They reversed the magnetic field faster than the needles could follow. Imagine a stadium full of people all leaning one direction, comfortable in their seats. Now yank the entire stadium around so fast that everyone stays frozen mid-lean, and suddenly they're all leaning the wrong way, straining against seats that have flipped underneath them. That is what happened to the nuclear needles. An instant before, they sat in the low-energy seat. An instant after, because the field had reversed, that very same lean now counted as the high-energy seat. The crowd had been flipped upside down without moving a muscle. In a single flick, Purcell and Pound had built a population inversion. More needles in the high seat than the low, the impossible waterfall running upward inside a chip of ordinary salt, and for a few brief moments before the crystal could relax, those nuclei sat at a genuine negative temperature, hotter than infinity, trapped in a lab, on purpose, for the first time in human history. They watched it happen through their radio equipment, and the signal came back inverted, a mirror image of the normal reading, the unmistakable fingerprint of a flipped crowd. The needles were not slowly warming or cooling. They had leapt clean over infinity to the far side of the temperature scale, and were now sliding back down through the negative numbers as the crystal relaxed toward normal. The whole strange state lasted only a short while. The inverted crowd could not hold. The nuclei gradually traded their energy with the rest of the crystal, toppled back into the low seat, and the temperature climbed back through infinity to an ordinary positive value. But for those few minutes, negative temperature had stopped being a line in a theory paper. It had become a thing that happened on a bench, in a building, in the real world. Purcell and Pound had caught the ghost. Yet catching a thing and convincing the world it is real are two very different battles. Because when they described what they had done, a storm of objection was waiting. Many physicists flatly refused to believe that a temperature could be negative at all, and one brilliant colleague set out to explain exactly how the trick worked. Slow down and savour the trick, because the whole miracle hides in one impossibly fast motion. The needles never had to climb. That is the part people miss. You might imagine that to reach the high-energy seat, Each nuclear needle would have to be laboriously lifted one by one up and over into its strained position. That would take enormous effort and careful energy for every single needle in a crowd of countless trillions. Purcell and Pound skipped all of it with a single reversal. They did not move the needles at all. They moved the seats. Think of the magnetic field as defining which lean is comfortable and which lean is strained. Point along the field, low energy, comfortable. Point against it, high energy, strained. The needles had settled comfortably. Then, by flipping the entire field in an instant, the experimenters swapped the meaning of every seat underneath the frozen crowd. The comfortable lean became the strained one. The whole army of needles, without twitching, found itself in the high-energy state, because high and low had traded places around them. Here is a way to feel it. Imagine a hillside covered with balls, all resting in little dips perfectly at rest. Now flip the entire hillside upside down in a flash. Every ball is suddenly perched on a peak instead of nestled in a valley, even though not a single ball rolled anywhere. You did not lift the balls. You inverted the landscape. Gravity that once held them down now wants to fling them off. That is the elegance of the flipping field. It creates a population inversion for free by rewriting the map rather than marching the crowd across it. In one snap, an ordinary bottom-heavy crowd becomes a top-heavy one, and a positive temperature vaults across infinity into the negative. The reason it works at all comes back to the ceiling. These nuclear needles have exactly 2 seats and nothing above, so flipping the field cannot send them scattering up an endless staircase. It can only pin them against the top in that packed, inverted hotter-than-fire arrangement. A capped system is the only kind that can be flipped this cleanly, and the nuclei in that little salt crystal were capped as tightly as any system in nature. There was one more piece of luck baked into the choice of crystal. The nuclear needles talked to each other very quickly, sharing energy among themselves almost instantly, so the whole crowd agreed on a single temperature right away, even a negative one. But they talked to the surrounding crystal very slowly, leaking their energy away only gradually. That gap in timing bought Purcell and Pound their precious window. The inverted crowd could exist, agree on its impossible temperature, and be measured, all before it drained back to normal. So the trick was really 3 tricks stacked together. A system with a ceiling so the crowd could invert, a fast field reversal so the inversion happened in an instant, and a slow leak to the outside world so the strange state lasted long enough to catch. It was a beautiful piece of work, but a beautiful experiment does not settle a war, and a war was exactly what erupted next. The moment Purcell and Pound claimed a negative temperature, a young theorist realized the idea needed a proper foundation, or skeptics would tear it apart. His name was Norman Ramsey, and he set out to prove, once and for all, whether a temperature below 0 was real physics or a clever illusion. A strange result needs more than a clever experiment. It needs a rock-solid theory, or the doubters will bury it. Norman Ramsey set out to build that rock. Ramsey was a young physicist orbiting the same Harvard world as Purcell and Pound, and he had helped think through the flipped crystal experiment. He understood at once that something profound had happened in that chip of salt, but he also understood the danger. When you announce a temperature below 0, every careful scientist in the room folds their arms and says, "That is nonsense. Temperature cannot do that." And unless you can answer them with airtight logic, your discovery gets filed away as a mistake or a trick of words. So Ramsey went back to the deepest foundations of the science of heat, the rules that govern energy and disorder, and he asked a simple, ruthless question. Do these rules actually forbid a negative temperature, or do people just assume they do because they have never met one? He worked through it line by line, and he found that the foundations did not forbid negative temperature at all. The core rule was only this: temperature comes from the way disorder changes as energy changes. Nowhere in the deep logic does it say disorder must always rise with energy. That was an assumption people had smuggled in from everyday experience, because everyday matter has no ceiling. Remove the assumption, allow a system with a top, and the very same rules calmly permit disorder to fall as energy rises, and temperature to go negative. Ramsey laid out the exact conditions required. First, the little pieces of the system must talk among themselves fast enough to agree on a single temperature, so the word means something at all. Second, there must be a ceiling, an upper limit on the energy the system can hold. Third, the system must be walled off well enough from the ordinary world that its strange state can survive for a while. Meet all three, and negative temperature becomes a legitimate, well-behaved member of the temperature family, no paradox at all. He went further, and this is the part that seals the story. He showed that every great law of heat still holds perfectly in the negative temperature realm. Energy is still conserved, heat still flows in a well-defined direction, nothing breaks, you do not get free energy or perpetual motion. You simply get a new stretch of the temperature scale, sitting past infinity, obeying all the same rules as the ordinary stretch below. With that, Ramsey turned a startling lab curiosity into solid, respectable physics. He gave the strange crowd a proper home in the theory, a full accounting of when it can appear and how it behaves. After his work, a physicist could say the words negative temperature without flinching, and point to a rigorous framework instead of a magic trick. But not everyone surrendered easily. The idea was so counter to intuition that even brilliant senior scientists refused to accept it, and one of the most respected thermal physicists in the world, a man whose name carried enormous weight, was about to corner Ramsey and try to talk him out of the whole thing, face to face, in the halls of Oxford. A few years later, Ramsey travelled to Oxford, and there a famous skeptic tried to prove him wrong to his face. The skeptic was Sir Francis Simon, one of the towering figures in the physics of extreme cold and heat, a man who had spent his life mapping the behaviour of matter near absolute zero. His instincts were legendary, honed over decades of careful work, and his instincts told him that this business of negative temperature had to be a mistake. Temperature below zero simply offended everything he knew. Colder than the coldest, above infinity. It sounded like a confusion of symbols, a place where the math had wandered off from reality. So Simon sat Ramsey down and pressed him. He raised objection after objection, drawing on his deep command of the subject, trying to expose the flaw he was certain must be hiding somewhere in the argument. This was a genuine test. Simon was a master, no crank at all, and if the idea had a crack, he was exactly the man to find it. Ramsey held his ground. Every time Simon pushed, Ramsey answered with the foundations he had rebuilt so carefully. Negative temperature needs a ceiling on energy, and the nuclear needles have one. It needs the pieces to agree on a temperature, and they do. It needs isolation, and the slow leak to the crystal provides it. Under those conditions, the rules of heat permit exactly this, and no law is broken. Point by point, Ramsey showed that the strange result flowed as a clean consequence of the very principles Simon himself had spent a lifetime trusting. The argument went on at length, two serious minds circling the same strange idea, one determined to break it and one determined to defend it. And slowly, remarkably, Simon came around. The master skeptic became convinced. He accepted that Ramsey was right, that negative temperature was a valid and honest thermodynamic state, and he even urged Ramsey to write up the complete theory so the rest of the world could be convinced too. That moment mattered enormously, when one of the most respected authorities in the field looks hard for the flaw, fails to find it, and changes his mind. The idea graduates. It stops being a fringe claim whispered about at conferences and becomes accepted physics. Simon's conversion was a seal of approval from the highest court in the land. Ramsey took the advice and wrote the full theory, a careful paper that remains a landmark to this day. In it he stated the conditions for negative temperature, proved it obeyed all the laws of heat, and closed the door on the easy objections for good. After that, the concept stood on firm ground. A little strange, yes, but real and here to stay. So within a handful of years, negative temperature had gone from a whirlpool prediction almost no one believed, to a flipped crystal on a Harvard bench, to a rigorous theory that survived the hardest cross-examination the field could throw at it. And here is a quiet twist that most people never realize. This exotic, hotter-than-infinity idea was not locked away in rare experiments. It was hiding inside a device that would soon appear in classrooms, checkout counters, and living rooms all over the world. A machine that runs, secretly, on a flipped crowd. The laser. The strangest fact in this whole story might be this. You have almost certainly held a negative temperature system in your hand. Every laser, from the pointer in a lecture hall to the scanner at a grocery store, runs on the very same flipped crowd that Purcell and Pound built in their crystal. The technology that fills modern life secretly depends on pushing atoms past infinity on the temperature scale. Here is how a laser works, stripped to its bones. Inside the laser sits a material full of atoms, and those atoms can hold different amounts of energy, sitting in a low seat or jumping to a high seat, much like our little compasses but with light instead of magnetism. Normally the crowd is bottom heavy. Most atoms rest in the low seat. That is the natural ordinary positive temperature shape. To make laser light, you have to flip that crowd. You pump energy into the material, hard, driving atoms up into the high seat, faster than they fall back down, until finally more atoms sit high than low. The crowd inverts, the waterfall runs upward. Physicists who build lasers call this exact condition a population inversion. The same shape, the same impossible top-heavy pattern we have been chasing this whole time, and a population inversion, as we now know, is a negative temperature. The heart of every working laser, in the instant it produces its beam, sits on the far side of infinity, hotter than any positive temperature in the same strange realm as the flipped salt crystal. Why does inverting the crowd make light? Because once the atoms are jammed into the high seat, they are desperate to fall, and when one atom falls and releases a particle of light, that light nudges its packed neighbours to fall too, each releasing more light, perfectly in step, all the same colour, all marching in the same direction. A tiny trigger becomes an avalanche of identical light. That marching unified avalanche is a laser beam. It is only possible because the crowd was flipped upside down first. So the clean, focused, powerful beam of a laser is, at its source, the light shed by a negative temperature crowd tumbling back toward normal. The whole device is a machine for building an inverted population, holding it and harvesting the flood of light it pours out as it collapses. This means negative temperature is running right now in millions of devices around the planet, far from a rare laboratory freak visited once and shelved. Every laser show, every fibre optic cable carrying your messages across oceans, every barcode scan, every laser used in surgery and manufacturing leans on a crowd of atoms briefly living beyond infinity. The exotic became ordinary without anyone noticing. The early pioneers even saw the connection. The same insight that let Purcell and Pound flip their crystal fed directly into the ideas that made stimulated light amplification possible, the very foundation of the laser. Flipping a crowd and squeezing light out of it are two faces of the same physics. Yet through all of this, from whirlpools to crystals to lasers, one crucial detail set a hard limit on what could be done. Every negative temperature system anyone had ever made lived inside spin, inside those tiny magnetic needles or their light-carrying cousins, never in the raw motion of atoms flying through space. And there was a deep, stubborn reason why. Motion, unlike spin, seemed to have no ceiling at all, which meant the true prize stayed just out of reach for 60 years. Before we chase that 60-year wall, sit with one consequence of a negative temperature that feels like a magic trick, because it reveals just how hot these systems truly are. Bring a negative temperature system into contact with anything ordinary, and heat gushes out of it. Always outward, never in. It cannot absorb heat from a normal object no matter how hot that object is, because there is nothing in the ordinary world hot enough to feed it. It sits above them all. Line up the everyday world and this is what you find. An ice cube, a warm room, a candle, a furnace, the surface of the sun. All of them are ordinary, positive temperature objects ranked from cool to blazing. Now set a negative temperature crowd beside any one of them. Heat flows from the crowd into the object. The crowd tries to warm the ice cube, yes, but it also tries to warm the candle and the furnace and even the surface of the sun. To all of them, it is the hotter partner. The exchange booth explains why, and it is worth seeing sharply. Heat always flows from high temperature to low. On the true scale of hotness, every positive temperature, no matter how large, sits below every negative one. So when the flipped crowd meets ordinary matter, energy slides from the crowd, which is higher on the ladder, down into the ordinary object, which is lower. The strange minus sign guarantees the crowd is always the source, never the sink. Picture the flipped crowd as a stadium jammed against its highest row, every fan straining at the ceiling, desperate to tumble back down toward empty seats below. Now open a door between that packed top-heavy stadium and an ordinary bottom-heavy one next door. Energy rushes through the door in one direction, from the crowd that is bursting at the top toward the crowd with room at the bottom. The flipped stadium empties its energy outward, because it is stuffed as full as a system can be and everything else has space to spare. The pioneers who first made these states described this outflow in exactly those terms. A negative temperature system, they said, is intensely hot in every sense, and it gives up its energy to any ordinary system placed in contact with it, decaying back toward normal by passing through infinite temperature on the way down. This is why the phrase hotter than infinite heat is plain truth. Hand a negative temperature crowd to the universe, and it behaves like the hottest object present, no matter what else is in the room. It warms the stars. It cannot be warmed by anything. It is the top of the ladder, and everything flows away from the top. For decades, though, this magnificent behavior could only be seen in spin, in the flip of a nuclear needle, in the pump of a laser, always in that hidden inner property of particles, never in their outright motion, their speed, their flight through space. And motion is where temperature was born. Motion is the jiggling, bouncing dance we started this whole journey with, to make atoms genuinely hotter than infinity in their motion. In the real jostling of particles through space, physicists faced a barrier that had blocked them since the days of that little salt crystal. Motion, it seemed, could always speed up. Motion had no top row, and without a ceiling, the trapdoor stays welded shut. Here was the problem that stopped everyone. Spin has a ceiling. Motion does not. Return to the difference between the two. A nuclear needle, a spin, has only two seats. Point one way or the other, low energy or high, and nothing above. That built-in ceiling is what let Purcell and Pound flip their crystal. The crowd could invert because it had a top to pile against. Now think about an atom simply flying through space. Its energy lives in its speed, and speed has no natural limit. An atom can crawl, or cruise, or race, or scream along faster and faster with no top gear. The staircase of motion climbs forever. There is no highest row for the crowd to jam against, and without a highest row you can never invert the crowd, never flip it top-heavy, never push it past infinity into negative temperature. So for 60 years, negative temperature stayed locked inside spin. Every example, from the salt crystal to the laser, relied on some hidden inner property with only a few seats, a natural ceiling handed over by nature. The moment you tried to make the actual motion of atoms go negative, the ceiling vanished, the staircase ran to the sky, and the whole trick fell apart. This bothered physicists deeply, because motion is where temperature truly lives. The jiggling, the bouncing, the flying of particles through space is the original meaning of hot and cold, the very thing we started with. Negative temperature and spin was marvellous, but it always carried an asterisk. It was negative temperature in a special, tucked-away corner of a system, not in the raw headline sense of atoms moving too hot to imagine. The real prize, a genuine negative temperature in the motion of a gas, sat behind a wall no one could climb. To scale that wall, you would need to do something that sounds absurd. You would need to build a ceiling for motion itself. You would need to trap atoms in such a way that their motional energy had a hard maximum, a highest possible speed state, a top row for the flying crowd to jam against. Give motion a ceiling, and you could flip it, just like a spin. Fail, and the endless staircase would defeat you forever. For a long time that seemed hopeless. How do you cap the speed of an atom? How do you tell a flying particle, this fast and no faster, with no higher gear allowed? Ordinary space offers no such limit. In an open box, a gas can always find a faster arrangement, always climb higher, always stay bottom heavy. The wall held. But physics had been quietly developing a new kind of tool, a way to reshape the very rules that govern how atoms are allowed to move, a cage woven out of light rather than a physical box with walls, a structure that could hand motion the one thing it never had, a ceiling. A team in Germany saw the possibility. They realized that if they trapped atoms inside a precisely built lattice of laser beams and tuned the trap just so, they could give the motion of a real gas a genuine upper limit. They could build the top row that motion always lacked. And if they could build the ceiling, they could flip the crowd and drag negative temperature out of spin and into the open, into the raw motion of atoms for the very first time. Around the year 2013, a group of physicists in Germany set out to do what 60 years of work had never managed. They aimed to make the motion of a real gas hotter than infinity. The work centered in Munich, at a laboratory led by researchers steeped in the art of controlling ultra-cold atoms. Among the driving figures were Ulrich Schneider and Simon Brown, working alongside a team including the renowned atomic physicist Emanuel Bloch. These were people who had spent years learning to cool atoms to the very edge of absolute zero and to steer them with light as gently as a shepherd steers a flock. If anyone could build a ceiling for motion, it was a group with this level of control. They understood the challenge exactly. To flip the motion of a gas into negative temperature, they needed three things at once, all in the same cloud of atoms, all under perfect control. They needed a ceiling on the energy, so the crowd could invert. They needed the atoms to talk to each other and agree on a temperature, so the word meant something. And they needed to hold the whole fragile state together long enough to measure it, before it collapsed back to normal. This was the same recipe Ramsey had written down decades earlier, now demanded for raw motion instead of spin. The ceiling was the hard part, the wall that had stopped everyone. Motion has no natural top. So the team's central insight was to stop using ordinary open space, where atoms can always fly faster, and instead trap the atoms inside a carefully engineered structure that would impose a maximum on their motional energy. They would not let motion run up an endless staircase. They would build a staircase with a final step. Their tool was a lattice of laser light, a topic we will open up next, which slices space into a grid and changes the rules of how atoms are allowed to move through it. Inside such a grid, motion no longer climbs forever. It develops a ceiling, a highest energy state, a top row at last. That was the key that could unlock the trapdoor for motion. But building the ceiling was only the first step. They also had to invert the crowd, to jam the atoms against that new top row, using a clever reversal of the forces holding the gas together, echoing in spirit the field flip that Purcell and Pound had used on their crystal. And they had to do it all with a cloud of only about 100,000 atoms, chilled to within a hair of the coldest temperature nature allows, held in an ultra-high vacuum, isolated from every stray disturbance that could ruin the delicate state. The stakes were more than a single strange measurement. If they succeeded, they would do far more than add another example to the list of negative temperature systems. They would drag the phenomenon out of its 60-year hiding place in spin and plant it firmly in the motion of a real gas, the original home of temperature itself. They would make atoms genuinely, motionally hotter than infinity for the first time in history. To pull it off, they first had to master the strangest cage in modern physics, a crystal made of pure light instead of matter, able to hold atoms like eggs in a carton and rewrite the rules of their motion. That cage is where the impossible became buildable. To trap their atoms and cap their motion, the team built a crystal out of nothing but laser beams. Picture two laser beams of the same colour aimed straight at each other, meeting head-on. Where they overlap, their waves add and cancel in a fixed pattern, creating a row of bright spots and dark spots, evenly spaced, standing perfectly still. Now cross-beams from several directions, and those bright and dark spots multiply into a full three-dimensional grid, a lattice of light dots repeating through space like a checkerboard, extended in every direction. Physicists call it an optical lattice, a crystal woven from light instead of atoms. This lattice of light acts like an invisible egg carton. Each bright or dark spot becomes a little pocket, a dimple where an atom can settle and rest. Sprinkle a cloud of ultra-cold atoms into this grid, and they drop into the pockets, one region of the carton after another, arranging themselves into a neat, orderly array held in place by nothing but carefully shaped light. An ordinary crystal holds its atoms with electric forces between them. This crystal holds its atoms with a gentle push and pull of laser beams, and the spacing and depth of its pockets can be tuned at will simply by adjusting the light. That tunability is the whole point. In an ordinary open gas, an atom can fly at any speed, climbing the endless staircase of motion with no ceiling. But inside a deep optical lattice, the rules change completely. An atom can no longer just accelerate freely. To move, it has to hop from one pocket of the egg carton to the next, and the light decides how easy or hard those hops are. The motion is no longer a smooth, open staircase. It becomes a set of allowed states with a bottom and, crucially, a top. There it is. The ceiling. Inside the lattice, the motional energy of the atoms has a highest possible value, a top row for the flying crowd to jam against. The light has handed motion the one thing it never had in open space. The endless staircase has been replaced by a staircase with a final step, exactly what negative temperature requires. This is a genuinely astonishing tool. Physicists can build a repeating grid of light, drop atoms into it, and reshape the fundamental rules of how those atoms are allowed to move, all by tuning laser beams. They can make the motion behave as if it lives in a small capped ladder rather than an open sky. And once motion has a ceiling, it can in principle be flipped, just as spin can, inverted into a top-heavy crowd sitting past infinity. The optical lattice had become common in laboratories for other reasons, as a way to build artificial crystals and study how atoms behave in orderly arrays. But the Munich team saw in it the missing ingredient for the 60-year puzzle. The lattice was the ceiling, it was the wall breaker. It could give a real, moving gas the capped energy landscape that only spin had ever enjoyed. With the cage of light ready, one enormous task remained before any flip could happen. The atoms had to be made unimaginably cold and unimaginably still, chilled to the very threshold of absolute zero, so that their delicate state could be controlled with the precision this experiment demanded. And cooling a cloud of atoms that close to the coldest possible cold is a feat that pushes human technology to its absolute limit. Before they could flip anything, the team had to make their gas colder than the darkest depths of space. The atoms they chose were potassium, an ordinary metal on the shelf, but in the lab they worked with a cloud of only about 100,000 of these atoms, a puff of gas so thin it would be invisible, floating in a chamber emptied of nearly every other particle. That emptiness matters. The chamber was an ultra-high vacuum, cleared of stray air until it held fewer particles than the space between planets, so that nothing from the outside world could bump the delicate cloud and ruin it. Then came the cooling, and the numbers here strain belief. The team chilled these atoms to less than 1/1,000,000th of a degree above absolute zero, colder than any natural place in the entire known universe. The gaps between galaxies, warmed faintly by the leftover glow of the beginning of the cosmos, sit far hotter than this. In that little chamber in Munich, the team had built one of the coldest spots that has ever existed anywhere, at any time. How do you cool a gas that far? No freezer built from ordinary matter could ever reach these depths, because the freezer itself would be blisteringly hot by comparison. Instead, physicists cool atoms with light and with patience, in stages, each one shaving away a little more motion. The first trick uses laser beams as a kind of molasses, aim beams at the atoms from all directions, tuned just right, and every time an atom tries to move, it runs into light that gently pushes back, slowing it down. The atoms wade through this glow as if through thick syrup, losing speed with every step, their frantic jiggling calming towards stillness. This alone brings them from room temperature down to a whisper above absolute zero. The final stage is even cleverer, and it works by sacrifice. The team lets the hottest, fastest atoms escape from the trap, deliberately, like letting the steam rise off a hot cup of coffee. As the fastest atoms flee, they carry away more than their share of energy, and the ones left behind settle to a lower temperature. Do this again and again, letting the warmest escape each round, and the survivors grow colder and colder until the remaining cloud sits at the very threshold of the coldest possible cold. At that point, the potassium atoms are barely moving at all. Their jiggling has nearly stopped. The crowd sits packed into the lowest seats, quiet and orderly and ready. This is the calm before the flip, the coldest starting line imaginable, a cloud so still and so cold that the experimenters can now steer it with exquisite precision. And precision is everything here, because the next move is delicate almost beyond words. They have to reverse the forces holding the gas together in exactly the right way, so that the atoms leap cleanly across the temperature scale instead of scattering into a warm, ordinary mess. So there they were, 100,000 potassium atoms caged in a lattice of light, chilled to a hair above absolute zero, sitting bottom-heavy in the lowest seats with a fresh ceiling built above them by the crossing lasers. Every ingredient Ramsey had listed assembled at last for motion instead of spin. All that remained was the flip itself, the single decisive move that would turn the crowd upside down and drag a moving gas across infinity into the negative. Now came the decisive move. The team turned the trap inside out, and the frozen crowd leapt across infinity. To understand the flip, picture the forces shaping the cloud. The atoms sat in a gentle bowl, a trap that pulled them toward the centre and kept them gathered, like marbles resting in the bottom of a rounded dish. In this bowl, low energy meant sitting still at the centre, and the crowd naturally settled there, bottom heavy, cold, ordinary. On top of that, the atoms interacted with each other in a way the team could also control, tuning whether they pushed apart or pulled together. The flip reversed these forces. In a swift, carefully timed move, the team turned the bowl into a hill. What had been a dish pulling atoms toward the centre became a dome pushing them away from it, and at the same instant, they retuned the interactions between the atoms to match. The entire energy landscape flipped over, top for bottom, in one coordinated stroke. This is the same deep trick Purcell and Pound used on their crystal, translated from spin to motion. They did not laboriously push each atom up into a high-energy state. They inverted the landscape underneath the whole crowd at once, an arrangement that a heartbeat earlier counted as low energy, sitting calmly in the bowl suddenly counted as high energy, perched on the dome. The crowd, without scattering, found itself jammed against the top of the newly built ceiling. Bottom heavy became top heavy in a single flip. Return to the image of balls resting in valleys on a hillside, and then flipping the entire hillside upside down so every ball perches on a peak. That is precisely what the Munich team did to the motion of their gas. They flipped the landscape so fast and so cleanly that the atoms had no time to spill. They stayed put while the world turned over around them, and in doing so they crossed from an ordinary positive temperature up through infinity and out the other side into the negative. The optical lattice was what made this possible. Without the ceiling the light provided, flipping the bowl into a hill would have simply flung the atoms into faster and faster motion, up the endless staircase, staying bottom heavy forever. But with the lattice capping the motional energy, the flipped crowd had a top row to jam against. The inversion took hold. The gas, in its raw motion, now sat past infinity, hotter than any positive temperature, for the first time in the history of the world. And crucially, the atoms still talked to each other. They shared energy among themselves and settled into a genuine, agreed-upon temperature, a real thermal state, not a random jumble. That is what made it a true negative temperature rather than a fleeting accident. The crowd had reached equilibrium on the far side of infinity, a stable, self-consistent, hotter than everything arrangement of a real moving gas. The whole event unfolded in the blink of an eye and had to be caught before it faded, because a negative temperature gas, like the flipped crystal before it, wants to leak its energy away and tumble back to normal. So the team had built a way to photograph the crowd at the decisive instant, to freeze the impossible waterfall in an image and read off its shape. What that photograph revealed was the proof, the unmistakable fingerprint of a crowd that had climbed to the top and jammed against the ceiling, and it looked like nothing an ordinary gas has ever produced. When the team took their picture, they saw the crowd standing exactly where no ordinary gas can ever stand, at the very top. To read the state of their atoms, the physicists used a technique that reveals how fast the atoms are moving and in what pattern. They release the cloud and let it expand, then capture an image, and from the way the atoms spread, they can reconstruct the shape of the crowd across the ladder of motional energy. It is like taking a census of the stadium, counting how many fans sit in the low seats and how many in the high. For an ordinary cold gas, the census comes back exactly as you would expect. The atoms cluster in the low energy states, packed near the bottom of the ladder, thinning out toward the top, bottom heavy, the natural settled shape. In the image, this shows up as a tight, calm clump gathered at the low energy center, the fingerprint of a normal, positive temperature crowd. For the flipped gas, the census came back inverted. The atoms had gathered in the highest energy states, packed against the top of the ladder, at the very edge of the ceiling the lattice provided. Top heavy, the impossible waterfall frozen in a photograph. In the image, the atoms formed sharp peaks, sitting precisely at the upper limit of allowed motion. the highest rungs, where an ordinary gas would show almost nothing at all. That inverted census was the proof, a crowd of real moving atoms sitting stably in the higher seats they were allowed to reach, more of them at the top than the bottom. No positive temperature can draw that picture, only a negative one. The photograph showed in plain sight a moving gas that had crossed infinity and settled on the far side, and the sharpness of the peaks carried a second message. The atoms had done far more than scatter randomly into high seats. They had organised, gathering into crisp, coherent clusters at the top of the ladder, a sign that the crowd had truly reached a settled, orderly thermal state at negative temperature, calm and coherent rather than chaotic. The gas was in genuine equilibrium, hotter than everything, calm and self-consistent in its impossibility. Hold the full weight of this image in your mind. A cloud of 100,000 atoms, chilled to less than a millionth of a degree above the coldest possible cold, sitting in a cage of light, and yet arranged in a pattern that means, on the true scale of heat, they are hotter than the surface of the sun, colder than deep space and hotter than a star at the very same moment, depending only on which meaning of temperature you use. And the honest meaning, the one that governs the flow of heat, says hot. This was the first time in history that a negative temperature had been reached in the motion of a real gas, in the outright motion of particles flying and hopping through space, the original meaning of hot and cold, rather than in the hidden spin of nuclei or the pumped atoms of a laser. The 60-year wall had finally fallen, but making the impossible crowd was only the beginning of the strangeness, because a gas that sits at negative temperature does far more than carry a weird label. It behaves in ways that seem to defy the deepest instincts of physics, starting with a pressure that points the wrong way, a gas that should crush itself into a point, yet calmly refuses. Pause on the magnitude of what fell that day, because it reshaped a rule that had stood since the birth of the study of heat. For as long as anyone had understood temperature as the jiggling of particles, that jiggling had only ever run one way. Faster meant hotter, and the fastest possible arrangement was simply the hottest ordinary state. No one had ever seen the motion of a gas climb past infinity and settle into a top-heavy crowd, because motion in open space has no top to settle against. The very idea of a gas that was motionally hotter than infinite heat had lived only in theory, an asterisk beside the spin experiments, a prize behind a wall. The Munich result tore the asterisk away. It proved that the strangest stretch of the temperature scale, the realm beyond infinity, was not confined to some tucked-away inner property of particles. It could be reached in the headline sense, in the raw motion of a real gas, if only you were clever enough to build a ceiling for that motion out of light. Temperature had been dragged, in full, into the negative, in the one arena where it was born. That achievement did more than complete a 60-year quest. It opened a door to entirely new physics, because a gas at negative temperature does far more than wear a strange number. It behaves in genuinely new ways, ways that let scientists explore corners of nature that were previously locked shut. Consider what it means to have a stable, controllable gas that sits on the far side of infinity. Physicists can now build such a gas on demand, hold it, measure it, and probe how matter behaves in a regime that simply does not occur naturally on Earth. It becomes a laboratory for the impossible, a way to test ideas about heat, order, and energy in a place the ordinary world never goes. The negative temperature gas is a new kind of material, with its own rules and its own surprises, and the surprises are immediate. The very first one overturns something you might think is unbreakable, the way a gas pushes on its surroundings. Every ordinary gas pushes outward. Pump air into a balloon, and it strains against the rubber, shoving out in all directions. That outward shove is pressure, and it comes from the atoms bouncing against the walls. Heat the gas, and it pushes harder. Every gas you have ever met wants to expand, to fill more space, to push out. A gas at negative temperature does the opposite. It pulls inward. Its pressure points the wrong way. Instead of straining to expand, it strains to contract, as if the gas were trying to collapse toward a point rather than spread out. This is negative pressure, and it sounds like a recipe for disaster. A gas that pulls itself inward should, by every ordinary instinct, crush itself into oblivion. Yet it does not. The negative temperature gas the team built was stable, holding itself together in a calm, settled state, refusing to either explode outward or crush inward. A gas that by all rights should collapse under its own strange inward pull simply sat there, poised and stable, defying the fate you would predict for it. How can a gas pull inward and yet refuse to collapse? The answer touches one of the deepest mysteries in all of science, a force that seems to be doing something eerily similar on the largest scale imaginable, stretching across the entire universe. Look closer at this backward pressure, because the way the gas survives its own inward pull is a small miracle of balance. In an ordinary gas cooled and squeezed the right way, if the atoms attract each other strongly enough, disaster follows. The attraction wins, the gas clumps, and it collapses inward, crushing toward a dense knot. Physicists had long known that a gas of attracting atoms is prone to this kind of implosion. It is one of the things that makes such gases hard to hold. Turn the attraction up, and the cloud caves in on itself. The Munich team's flipped gas had exactly this kind of inward pull. The atoms were arranged so that they attracted one another, and the pressure pointed inward, both conditions that should have doomed an ordinary cold gas to collapse. By every rule of the positive temperature world, that cloud should have crushed itself into a dense clump and been destroyed. The negative temperature saved it. Here is the balance. The inward pull of the atoms, which would normally trigger collapse, was held in check by the strange thermodynamics of the negative temperature state itself. The very inversion that made the gas hotter than infinity also gave it a kind of backbone, a resistance to caving in. The two effects, the attraction that wants to collapse the gas and the negative temperature state that props it up, balanced each other into a stable standoff. The cloud held. This was one of the remarkable prizes of the whole experiment. The team had created a gas of attracting atoms that, in the ordinary world, could never have stayed stable. Only by pushing it past infinity into negative temperature could such a cloud exist at all without imploding. They had built a form of matter that positive temperature forbids, a stable gas held together in a state that should tear it apart, made possible only by living on the far side of the temperature scale. Think of it as a bridge that stays up precisely because it is being pushed and pulled by two enormous forces that happen to cancel. Remove either force and the bridge falls one way or the other, keep both in perfect opposition, and the bridge stands poised on a knife edge of balance. The negative temperature gas is that bridge, holding steady in a place where either force alone would spell ruin. And this points to something far larger than one clever experiment. The team realized that a gas with negative pressure, a substance that pulls inward, yet resists collapse and can fill its space in a stable, self-consistent way, resembles one of the most profound puzzles in the entire cosmos. Something out there, on the grandest scale, also seems to carry a strange pressure that points the wrong way, something that shapes the fate of the whole universe. The connection runs deeper than a loose poetic echo. The physicists who built the gas noted directly that negative temperature states carry negative pressure, and that this opens a door to studying in a tabletop chamber, behavior that mirrors a force astronomers have been struggling to understand for decades, a force woven into the expansion of space itself. That force has a name that has haunted physics since it was discovered: dark energy, and the strange little cloud of potassium atoms in a Munich lab might be a miniature echo of the thing that is pulling the entire universe apart. The universe is being torn apart and no one fully understands why. A cloud of flipped atoms may offer a tiny tabletop reflection of the culprit. Here is the cosmic mystery. Astronomers once assumed the universe, expanding since its birth, should gradually slow down, its outward rush braked by the gravity of all the matter pulling inward. That is the natural expectation. Gravity attracts, so it should be reeling everything back in, slowing the expansion over time. Instead, when astronomers measured carefully, they found the opposite. The expansion of the universe is speeding up. Galaxies are flying apart faster and faster, as if some force were actively pushing space to stretch. Scientists gave this unknown pushing force a name: dark energy. It fills all of space, and it acts like something with a pressure that points the wrong way, a negative pressure that drives space to expand rather than collapse. Dark energy is now believed to make up the majority of everything in the cosmos, and yet its true nature remains one of the deepest unsolved puzzles in science. We can measure its effects across billions of light years, and we still do not know what it is. Now recall the Munich gas. It carried negative pressure, a pressure pointing the wrong way, the same backward quality that dark energy seems to have on a cosmic scale. A stable substance that pulls, or pushes against the ordinary expectation, held together by its strange negative temperature nature. In a small glass chamber, physicists had built a material with a property that, until then, had mostly been discussed in the context of the entire universe. This is why the experiment excited people far beyond the world of ultra-cold atoms. It raised a tantalizing possibility. If you can build a stable substance with negative pressure on a laboratory bench, you might be able to study up close and under total control the kind of behavior that dark energy shows across the heavens. You could poke it, tune it, and watch how a negative pressure substance behaves, gathering clues about the grand cosmic mystery from a cloud you can hold in a single room. Be careful here, because the connection is an analogy, a resemblance, not a claim that the potassium cloud is literally the same stuff as dark energy. No one is saying the Munich team bottled the force expanding the universe. What they built was a system that shares a striking and important feature with dark energy, negative pressure in a stable form, and that shared feature makes the little gas a valuable model, a miniature stand-in, a way to explore in the controllable world of atoms a behavior that otherwise only shows up on the largest stage there is. That is the strange beauty of this whole line of physics, a phenomenon predicted from whirlpools, first caught in a chip of salt, hiding inside every laser, and finally dragged into the motion of a gas, turns out to brush up against the fate of the entire cosmos. The trapdoor beyond infinity opens onto questions as large as the universe itself, and the wrong-way pressure is only one of the mind-bending behaviors this new state unlocks, because a system that sits past infinity can also be plugged into a heat engine, the humble machine behind engines and refrigerators, and when you do, the numbers that come out seem to break the most sacred limit in all of thermodynamics, an efficiency that looks, impossibly, like more than perfect. Feed a negative temperature into a heat engine, and the machine appears to do something that should be flatly impossible. It seems to run better than perfectly. To feel the shock, start with an ordinary heat engine. Every engine that turns heat into useful work, from the one in a car to the turbine in a power plant, runs on a simple principle. It takes heat from a hot source, dumps some of it into a cold sink and pockets the difference as work. And there is an ironclad limit on how well it can do this, a ceiling on efficiency set by the temperatures of the hot source and the cold sink. No engine, no matter how cleverly built, can ever cross that ceiling. It is one of the most sacred limits in all of physics, a wall that has never been breached. That efficiency ceiling depends on the two temperatures. The hotter your source and the colder your sink, the higher the ceiling, but it always stays below 100%. You can never turn all the heat into work. Some must always be thrown away into the cold sink. That waste is the price the universe demands. Perfect efficiency, 100%, is forever out of reach for any ordinary engine. Now replace the hot source with a negative temperature system. Remember where negative temperature sits on the true ladder of heat, above every positive temperature, past infinity, hotter than anything ordinary. Plug that into the formula for the efficiency ceiling, and the arithmetic produces a startling result. The ceiling rises past 100%. On paper, an engine running between a negative temperature source and an ordinary cold sink can have an efficiency that appears to exceed perfect. It seems to extract more work than the heat you would naively expect. This sounds like the dream of every inventor who ever chased a perpetual motion machine, a device that gives more than it takes. And it is exactly the kind of result that makes careful physicists deeply suspicious, because free energy is supposed to be impossible. Here is the honest resolution, and it matters. The apparent leap past 100% is real in the arithmetic, but it does not mean you're getting something for nothing. The trick is that a negative temperature source is an extraordinary hard-won thing. All the energy and effort poured into flipping a crowd past infinity, into building and maintaining that impossible state, is part of the true accounting. When you tally everything honestly, no law is broken. No free lunch appears. The engine is simply exploiting a source that sits in a stretch of the temperature ladder so extreme that the ordinary efficiency formula produces a number above 1, with no perpetual motion and no real magic behind it. Still, the result is genuinely mind-stretching. It shows how thoroughly negative temperature scrambles our instincts. Limits we treat as absolute, ceilings we assume can never be crossed, bend into strange new shapes once you allow temperatures beyond infinity. The familiar rules still hold, but they dress themselves in costumes that look, at first glance, like miracles. Which raises an obvious and important worry. If negative temperature lets engines seem to beat perfection, and lets gases pull inward without collapsing, and lets atoms sit hotter than stars while colder than space, is it quietly breaking the laws of physics somewhere along the way? The answer is a firm and reassuring no, and understanding why not reveals just how deep and flexible those laws truly are. With all this strangeness piling up, it is fair to ask whether negative temperature cheats. It does not. Every great law of heat survives intact. This was the first thing serious physicists demanded, going all the way back to Ramsey's careful theory. If negative temperature broke the fundamental rules, it would not be a fascinating new stretch of the temperature scale. It would be a mistake, a sign that something in the reasoning had gone wrong. So the question was tested, hard, from the very beginning. And the verdict has held ever since. The laws stand. Take the most sacred rule first, the conservation of energy. Energy can never be created or destroyed, only moved around and changed in form. Negative temperature obeys this perfectly. When you flip a crowd past infinity, you do not conjure energy from nothing. You pour energy in, carefully, to jam the crowd against its ceiling. Every bit of energy is accounted for. When the flipped crowd relaxes and dumps heat into ordinary matter, that heat came from the energy you invested. The books always balance. Nothing appears from nowhere. Now the rule about disorder, the one that says the total disorder of the universe never decreases. This is the law people worry about most, because negative temperature involves disorder falling as energy rises inside the flipped system. But look at the whole picture, beyond the flipped crowd alone. To create and hold that inverted state, the experiment pushes disorder up elsewhere, in the lasers, the cooling machinery, the surrounding world. Tally everything together, and the total disorder of the universe still climbs, exactly as the law requires. The flipped crowd is a small pocket of falling disorder, paid for by a larger rise everywhere around it. Even the apparent miracle of the super-efficient engine obeys the rules, as we saw. The efficiency formula produces a number above 100% only because the source sits past infinity. But the full accounting, including the enormous cost of building that source, leaves every law intact. No perpetual motion, no free energy, just familiar physics wearing an unfamiliar disguise. This is the crucial point that makes negative temperature respectable rather than absurd. It is a genuine, lawful part of thermodynamics, rather than a loophole for cheating the universe, and it had simply been overlooked because ordinary matter, with its endless staircase of motion, never visits it. Give a system a ceiling, meet the conditions Ramsey laid out, and the same eternal laws that govern ice cubes and stars govern the flipped crowd too. They just allow a stretch of the temperature scale that everyday experience never reaches. There is something beautiful in this. The laws of heat turn out to be far more general than the world we normally see. They quietly permit temperatures beyond infinity, top-heavy crowds, backward pressures, and engines that look super efficient, all without a single contradiction. The universe was always built to allow these things. We just needed systems strange enough and physicists clever enough to walk through the trapdoor and see them. And yet, for all this careful accounting, not everyone agrees that negative temperature is truly real. Because in 2013, right after the Munich team announced their flipped gas, a pair of physicists published a bold and troubling claim. They argued that negative temperature is an illusion, a mirage born from choosing the wrong formula for disorder in the first place, and their challenge would ignite a fierce debate that strikes at the very meaning of temperature itself. Just as negative temperature seemed triumphant, two physicists stood up and declared the whole thing a mirage. Their names were Jörn Dunkel and Stefan Hilbers, and shortly after the Munich experiment made headlines, they published a challenge that landed like a thunderclap. Their claim was bold and unsettling. Negative absolute temperature, they argued, does not really exist. It is an artifact, a mistake that creeps in when physicists use a particular way of counting disorder. Choose a different, and in their view more correct, way of counting, and the negative sign vanishes. Every system, even one with a ceiling and a top-heavy crowd, would then have an ordinary positive temperature after all. This came from serious scientists making a serious technical argument about the very foundations of the science of heat, far from a fringe complaint by someone who misunderstood the physics. They were reaching back to the deepest question of all, the question of how you properly count the number of arrangements a system can take, the count that defines disorder, which in turn defines temperature. And they claimed the standard count, the one that produces negative temperatures, was the wrong one. The stakes were enormous. If Dunkel and Hilbert were right, then a great deal of what we have explored would need to be redescribed. The flipped crowds would still exist, the inverted photographs would still be real, but the label negative temperature would be a misnomer, a symptom of using the wrong bookkeeping. The whole exotic stretch of the temperature scale beyond infinity might be, in their telling, a kind of accounting error dressed up as a discovery. Their challenge divided the field. On one side stood the many physicists who had spent decades working with negative temperature, who had built the flipped crystals and the laser inversions and the Munich gas, and who insisted the concept was sound, useful, and real. On the other side stood Dunkel, Hilbert, and those persuaded by their argument, who insisted the whole edifice rested on a flawed choice made long ago. Papers flew back and forth. Rebuttals answered rebuttals. The debate grew sharp and technical, and at times heated in the ordinary sense of the word. What made the argument so stubborn is that it could not be settled by simply doing another experiment. Both sides agreed on what the atoms were actually doing. They agreed on the flipped crowds, the inverted census, the outflow of heat. Where they disagreed was on how to describe it, on which formula for disorder deserved to be called the true one, and therefore on whether the word temperature should carry a minus sign. It was a fight about the right language to wrap around the facts, rather than about the facts of the world themselves, and that is what makes this rebellion so revealing. It exposed that even something as basic as temperature, a word every child learns, rests on a choice, a definition, a convention that most people never think to question. Two brilliant camps could look at the very same cloud of atoms and, while agreeing on the atoms themselves, disagree about what to call their state. To understand the heart of their disagreement, we have to open up the two rival ways of counting disorder, two formulas born long ago from two legendary physicists, formulas that mostly agree about the everyday world but split violently apart when a system has a ceiling. At the centre of the fight sit two rival formulas for counting disorder, born from two giants of physics, and they disagree about whether temperature can ever go negative. Disorder, remember, is a count of arrangements. But it turns out there is more than one reasonable way to do that counting, and long ago two different recipes emerged. One recipe is usually credited to Ludwig Boltzmann, a founding father of the science of heat. His way of counting looks at how many arrangements a system has at a particular energy, right at that energy level. The other recipe traces to Josiah Willard Gibbs, another towering pioneer. His way of counting looks instead at how many arrangements a system has at that energy or any energy below it, adding them all up from the bottom. For the ordinary world, these two recipes barely differ. In a normal system with an endless staircase of energy, both ways of counting rise together as energy rises, and both hand you the same familiar positive temperatures. The difference between them is so tiny that for centuries it hardly mattered which one you used. The two recipes split apart only when a system has a ceiling. In a capped system, the one that can invert its crowd, the Boltzmann count starts to fall once the crowd bunches against the top, because there are fewer arrangements when everyone is jammed into the higher seats. Falling disorder as energy rises gives a negative temperature. That is the whole basis of everything we have explored. The Boltzmann recipe says, plainly, that negative temperature is real. The Gibbs recipe refuses to fall. Because it always adds up every arrangement from the bottom up to the current energy, its total keeps creeping upward even as the crowd inverts, since you are still piling more and more arrangements onto the growing sum, and if the count never falls, the temperature never goes negative. Under the Gibbs recipe, even a fully inverted top-heavy crowd carries an ordinary, if enormous, positive temperature. Negative temperature simply cannot happen. There it is, the core of the rebellion. Dunkel and Hilbert argue that the Gibbs recipe is the correct one, the truly consistent one, and that therefore negative temperature is an illusion produced by clinging to the Boltzmann recipe. The defenders of negative temperature argued back that the Boltzmann recipe is the one that actually matches how these systems behave, how heat flows out of them, how they act like the hottest things in the room, and that the Gibbs recipe, whatever its mathematical virtues, fails to capture the physics people actually observe. Both sides had real arguments. The Gibbs recipe has an elegant internal consistency that its champions prize. The Boltzmann recipe has a direct intuitive link to the observed behaviour of flipped crowds that its champions insist cannot be waved away. This is a genuinely deep disagreement, and it has not been tidily resolved to everyone's satisfaction. It reaches down to the foundations of how we describe heat, order, and energy, foundations most people assume were settled a century ago. And underneath the clash of formulas lies an even more basic and unsettling question, one that this whole debate forces into the open. What does the word temperature actually mean? The real thing beneath the number on a thermometer. Because if two careful definitions can disagree about the same cloud of atoms, then temperature is a subtler idea than any of us were ever taught. The debate forces a question most people never pause to ask. What is temperature really, once you strip away the thermometer? We began this journey by tearing temperature away from the warmth on your skin. Then we rebuilt it as a slope, the rate at which disorder climbs as energy climbs. That definition carried us across infinity into the negative and explained the flipped crowds, the outflowing heat, the whole strange landscape beyond the ordinary. It is a powerful, precise, working definition, and it is the one that gives negative temperature its meaning. But the rebellion of the two entropies revealed something humbling. That definition rests on a choice. The choice of how to count disorder in the first place. And reasonable, brilliant people can make that choice differently and arrive at different answers about the very same atoms. Temperature, it turns out, is a carefully constructed idea, built on foundations that can be laid in more than one way, rather than a single, obvious fact painted onto the world. So which definition is right? The honest answer is that it depends on what you want temperature to do. If you want temperature to predict which way heat flows when two systems touch, the definition that produces negative temperatures wins, because it correctly says heat pours out of a flipped crowd into everything else. That behaviour is observed, measured, real. By the test of the flow of heat, negative temperature earns its name. If instead you demand a definition with certain elegant mathematical properties above all else, you might prefer the recipe that forbids negative temperature and keeps every system positive. Each choice serves a different master. Neither is simply, obviously wrong. What this teaches is profound and a little unsettling. Temperature, one of the first scientific ideas any of us ever learned, is far deeper and more slippery than the number on a wall thermometer suggests. Underneath that familiar number sits a rich structure of definitions, conventions, and choices, most of which agree perfectly in the everyday world, and only reveal their differences in extreme exotic systems like a crowd flipped past infinity. The ordinary world is a place where all the reasonable definitions happen to agree, which is exactly why we never noticed they were separate ideas at all. Negative temperature is valuable partly for this reason. It is a stress test for our concepts. By dragging temperature to an extreme it never reaches in daily life, it exposes the hidden machinery underneath, the assumptions and choices we usually get to ignore. It shows us that even our most basic scientific words are built on scaffolding, and it invites us to look at that scaffolding clearly for perhaps the first time. And this is how physics often makes its deepest progress, by discovering new things in the world, and just as often by discovering that our old, comfortable ideas were hiding assumptions all along. The flipped crowd of potassium atoms did more than sit hotter than a star. It held up a mirror to the concept of temperature itself, and revealed how much we had taken for granted. There is one more surprise waiting, and it pulls the whole story back out of the laboratory and into the wider universe. Because for all the effort it takes to build a negative temperature by hand, with lasers and vacuum chambers and perfectly timed flips, nature may be quietly making these states on its own, in places far larger and wilder than any lab bench. For all the exquisite effort it takes to build a negative temperature in a lab, nature may be quietly making them on a scale that dwarfs any experiment. Remember where this whole idea was born. It first took shape in the mind of Lars Onsager, staring at whirlpools in a moving fluid, far from any laboratory. He predicted that a thin, bounded sheet of swirling fluid, with its capped energy, could climb past infinity and settle into large, calm, long-lived swirls at negative temperature. That prediction was about the natural behaviour of fluids, not about anything a physicist had to painstakingly construct. And that behaviour appears to be real, in thin, two-dimensional sheets of fluid where swirls are confined to a surface and their energy is capped. Small, chaotic vortices can gather themselves into big, orderly, persistent ones, exactly the sign of a negative temperature state. It is a possible clue to one of the enduring puzzles of fluids and weather, the way giant, stable swirls sometimes emerge from smaller turbulence rather than simply dissolving. Look up, and the possibilities grow even grander. Consider a cluster of stars or a galaxy held together by gravity. Gravity is a strange master, and systems bound by it can behave in ways that echo the negative temperature realm. Add energy to a cluster of orbiting stars in certain conditions, and instead of spreading out and cooling as an ordinary gas would, the system can contract and grow hotter in its core. A backward, counterintuitive response that shares deep mathematical kinship with the physics of capped, invertible systems. Astronomers have long known that self-gravitating systems break the comfortable rules of ordinary heat, and the language of negative temperature is one way to make sense of their strangeness. The thread connecting all of these, from whirlpools to star clusters, is the same ingredient we have chased from the beginning: a ceiling, a bound on the energy, so that beyond a certain point adding energy stops spreading the crowd and starts gathering it. Wherever nature builds such a ceiling, the trapdoor beyond infinity can crack open on its own, with no physicist flipping a switch. This reframes the whole story. Negative temperature may be far more than a fragile laboratory trophy, coaxed into being by lasers and vacuum and perfect timing. It may be a genuine, recurring feature of the natural world, showing up wherever the conditions are right, from the swirl of a fluid to the slow dance of stars around a galactic centre. The lab experiments are precious because they let us build and control these states cleanly, but the phenomenon itself may be woven through nature at every scale, hiding in plain sight in storms and starfields. That makes the humble cloud of potassium atoms in Munich something more than a curiosity. It becomes a key, a controllable, tunable example of a phenomenon that stretches from tabletop to galaxy, and a controllable example of anything strange is worth its weight in gold to physicists because it can be turned into a tool, a machine for exploring worlds we could never otherwise reach. Because once you can build a negative temperature gas on demand, you can use it as a stand-in, a simulator, to mimic other exotic systems that are far too hard to study directly, and that opens a door to designing and understanding materials that have never existed anywhere on Earth. Once you can build a flipped gas on demand, it becomes something extraordinary, a machine for imitating worlds we cannot otherwise reach. The idea is called quantum simulation, and it is one of the most powerful uses of ultra-cold atoms. Many of the most important puzzles in physics involve enormous crowds of particles interacting in complicated ways, like the electrons inside an exotic material. These systems are often impossibly hard to calculate, too tangled for even the greatest computers to fully predict. So physicists try a different approach. They build a clean, controllable copy of the puzzle out of ultra-cold atoms, and they let the atoms act out the physics directly, reading the answer off the behaviour of the cloud. The optical lattice is perfect for this. Recall that it is a crystal of light, a grid of pockets holding atoms in an orderly array, tunable at will. That grid can be made to mimic the grid of a real crystal, with the atoms standing in for electrons. By adjusting the lasers, physicists can dial the interactions up or down and watch how the crowd behaves, learning about real materials through their atomic imitations. Now add negative temperature to the toolkit, and the reach of the simulator expands dramatically. Every material and model has a range of temperatures over which it can be studied. Ordinary methods let physicists explore the positive temperature portion, from cold up toward infinity. But a whole territory of behaviour lives on the far side, in the negative temperature realm beyond infinity, and until you can flip the crowd, that territory stays locked. The ability to build negative temperature gases hands physicists the key to that locked half of the map. They can now simulate matter in regimes that were previously unreachable, exploring how model materials behave when pushed past infinity into the inverted realm. This matters because some of the most interesting and mysterious behaviours of matter may hide in exactly these hard-to-reach regimes. New kinds of order, new patterns of how particles arrange and move, new phases of matter that have no counterpart in the ordinary positive temperature world. By flipping their atomic crowds, physicists can hunt for these exotic states in a controllable model, gathering clues that could eventually guide the design of real materials with useful and surprising properties. Think of it as gaining access to a hidden wing of a vast museum. For a long time, physicists could wander only the ground floor, the positive temperature halls, studying the exhibits there. Negative temperature unlocks a staircase to an upper floor no one could previously enter, filled with displays of matter behaving in ways the ground floor never shows. The flipped gas is the key to that staircase, and physicists are only beginning to explore what waits above. So the strange cloud that started as a proof of a 60-year-old dream becomes a practical instrument, a way to expand the reach of quantum simulation into forbidden territory. The curiosity turns into a tool, and the tool becomes a window onto forms of matter that might one day reshape technology. And this is where the whole sprawling story begins to gather itself into a single, startling lesson. A lesson about the nature of heat, of extremes, and of the quiet assumptions we build our understanding upon. Because the deepest surprise of negative temperature is what the entire idea reveals about the shape of reality itself, far more than any single experiment, and about the strange truth that the hottest thing in the universe might be sitting perfectly still. Step back from the lasers and the debates, and negative temperature whispers something unsettling about time itself and about what it means for a system to be at rest. We usually picture equilibrium, the settled state a system relaxes into, as a kind of calm, ordinary place. A cup of coffee cools to room temperature and sits there. A gas fills its container evenly and stops changing. Equilibrium feels like the low, quiet, natural resting point of things, the bottom of a valley where everything comes to rest. Negative temperature complicates that comfortable picture. A flipped crowd, jammed against its ceiling, is also in a kind of equilibrium. It has settled into a stable, self-consistent, agreed-upon state. Yet it sits at the very top of the energy ladder, the opposite of a quiet valley floor. It is a resting point perched at the summit, a settled state that is maximally energized rather than minimally so. Equilibrium, it turns out, does not have to mean lying at the bottom. It can mean crowding at the top in a system with a ceiling. This stretches our sense of what a natural resting state even is. It shows that the settled equilibrium condition of a system depends entirely on the shape of its energy landscape, on whether that landscape has a ceiling and how the crowd fills it. Remove the assumption that energy climbs forever, and equilibrium can live in places our everyday intuition would never expect, high above infinity packed against a lid. Negative temperature also plays strange games with the flow of heat, which is deeply tied to our sense of time. The direction heat flows, always from hot to cold, is one of the clearest signposts of time's arrow. A flipped crowd sits at the top of the hotness ladder, so heat always flows out of it, never in, giving it a fixed and definite role in the direction of heat exchange. It is always the source, always the giver, a system whose place in the flow of heat is locked by its position beyond infinity. None of this breaks the deep laws that govern time and disorder as we have carefully established. The total disorder of the universe still rises. The arrow of time still points the same way overall. But negative temperature reveals that these grand principles are more flexible and more subtle than the simple slogans suggest. Heat from hot to cold, disorder always rising, equilibrium at the bottom, all remain true in the big picture, yet each hides exceptions and refinements that only appear when you visit the exotic realm beyond infinity. That is perhaps the greatest gift of this strange physics. It leaves the foundations standing and illuminates them at the same time, showing us their true shape by pushing them to their limits. It reveals that the rules we learned as children, hot flows to cold, everything settles down, are the everyday face of far richer principles. And it reminds us that reality is stranger and more supple than our instincts allow, that the universe permits states and behaviors we would have sworn were impossible. Which brings us at last to the single image that captures this entire journey. A picture that would have sounded like pure fantasy at the start, yet is now simple, established fact. The hottest thing in the known universe, hotter than any star, hotter than infinite heat itself, sitting frozen and nearly motionless in a quiet laboratory, colder than the space between the stars. Here, at the end, is the image to carry with you. Somewhere in a quiet laboratory sits the hottest thing in the known universe, and it is almost perfectly still. Gather everything we have travelled through into that single picture. A cloud of 100,000 potassium atoms, sealed in a chamber emptied of nearly all else, chilled to less than a millionth of a degree above the coldest cold that nature allows. By the reading on any ordinary thermometer, it is unimaginably frigid, colder than deep space, colder than anything the natural universe produces, and yet, by the true measure of heat, the one that governs which way energy flows, it is hotter than fire, hotter than the surface of the sun, hotter than infinite heat itself, colder than the void and hotter than a star in the same cloud. This is the honest, dual truth of what temperature really is, a genuine feature of nature rather than a paradox to explain away. On one scale, the everyday scale of jiggling motion, the atoms are barely moving, a frozen whisper of a gas. On the deeper scale, the scale of how energy and disorder trade against a ceiling, the crowd has been flipped past infinity into the searing realm beyond, where heat can only pour outward, where it stands above every star and every furnace in the cosmos. Trace the whole path that led here. It began by tearing temperature away from the warmth on your skin and rebuilding it as a slope, a trade between energy and disorder. It found a trapdoor hidden in that trade, opened only by a ceiling on energy, and followed the temperature dial as it climbed to infinity and wrapped around into the negative, into a place hotter than everything. It ran through a whirlpool prediction almost no one believed, a salt crystal flipped over a weekend, a fierce argument won in the halls of Oxford, and a secret hidden inside every laser ever built. It climbed a 60-year wall using a crystal made of light, flipped a real gas across infinity for the first time, and found a cloud that pulls inward yet refuses to collapse, echoing the dark force tearing the universe apart. It weathered a rebellion that questioned whether any of it was real, and emerged showing that even the word temperature rests on choices we never knew we were making. And it leaves us with a lesson far larger than any single experiment. The universe is built to allow things our instincts swear are impossible. Temperatures beyond infinity. Crowds that flip upside down. Heat that flows out of something ice cold on the surface. Equilibrium perched at the very top of the ladder rather than the bottom. All of it lawful, all of it real, all of it hidden just past the edge of ordinary experience, waiting for someone clever enough to build the ceiling and open the trapdoor. The next time you feel warmth on your skin, remember what temperature truly is. It is a slope, a trade, a pattern in a crowd of countless trembling particles, far from any simple substance or feeling. And remember that this quiet, everyday idea has a far side, a realm beyond infinity where the hottest things in existence sit frozen and still, waiting in glass chambers, patient and impossible, at the edge of the coldest cold that nature allows. The universe is stranger than we are built to imagine, and sometimes the strangest thing of all is the one sitting perfectly still,